Chapter 15, Section 3, Exercises 1, 2, and 3. In Exercise 1, which we will read through, we are supposed to evaluate the following line integral. Now we considered this vector field, this vector valued function, back in handout 15.1 in Exercise 3. And in this exercise, we found that the vector field f is conservative, and we did that by computing a potential function for the vector valued function. So, since f, the vector field, is conservative, by the fundamental theorem of line integrals, the value of the line integral is found by evaluating the potential for f at the endpoint minus evaluating the potential function at the initial point. So we have to make sure that we are noting the orientation of C. Back in 15.1, we found this function, lowercase f, to be a potential for the vector field, capital F. The endpoint is 6, negative 2, and lowercase f evaluated at 6, negative 2 is 864. The potential function, lowercase f, evaluated at the initial point is negative 1125. We subtract those results. We get an answer of 1989. In exercise 2, which we will read through as well, we are supposed to evaluate the following line integral. It's very easy to show that the vector field, capital F, is conservative. We have a test, and you can refer to 15.1 to see that theorem. Now, since capital F is conservative, and since C is a closed curve, the value of the line integral is 0. This notion is reinforced in the theorem just above. Let's look at exercise 3. Here we have a closed curve C, but the line integral is not necessarily 0. It's 0 if f is conservative. The partial of m with respect to y is equal to 1. The partial of n with respect to x is equal to y. Since the partial of m with respect to y does not equal the partial of n with respect to x throughout C, this means that f is not conservative. So we must parameterize the curve C and evaluate the line integral the old-fashioned way. For C1, this is a half circle of radius 4 centered at the origin, oriented in the positive direction. From basic trigonometry, this is an angle opening in the positive direction. While we are here, let's compute R1 prime. Let's look at C2, this line segment. We could take some time to parameterize this, and in my notes I explain how to do this, such that the domain of the parameterization for C2 does not overlap the domain for the parameterization of C1. But notice that along this curve C2, at every single point along here, the y-coordinate is 0. Look at F. On C2, F is equal to 0. Therefore, since f is the 0 vector on C2, the line integral of f over C is equal to the line integral of f over C1. Now, on C1, f is equal to 4 sine of t I, because this is y, plus x times y. Here's x, here's y. So it's plus 4 cosine of t times 4 sine of t, j. And f dot dr is the following. We multiply the I component of f with the I component of r prime. And we add the j component of f times the j component of r prime. So therefore, this is how the line integral shapes up. And I'll refer you to do the rest of this by reading through my handout. From here it's a Calculus 1 level integration problem, some basic U substitution.